Hi everyone, I am Suja Alex and I am presenting our research paper Digital Twin Based Dynamic Resource Provisioning using Deep Q Network on 6G enabled mobile edge networks, which is accepted at 17th International Conference on Communication Systems and Networks. This talk covers introduction, objective of proposed method, contributions, proposed method DT-DRP, proposed algorithm, simulation setup with the results and discussion. The development of 6G technologies is in progress, aiming to harness the terahertz spectrum to advance mobile communications and expand IoT capabilities. Mobile applications using 6G wireless systems have diverse requirements regarding latency, reliability, scalability, data rate, and user defined performance metrics. Digital twin technology creates real time digital replicas of physical entities, and this capability significantly impacts mobile networks to offer improved functionality and performance. By utilizing reinforcement learning, the model adopts and optimizes the resource allocation decisions in real time. The motivation of our work are developing a dynamic edge specific architecture with a digital twin and 6G enabled network while minimizing the communication and computational delay and energy usage reduction for mobile devices. Designing a dynamic resource provisioning technique at the edge server to meet the service needs of mobile users. The objective of digital twin based mobile edge network is to optimize the overall energy consumption by minimizing the sum of weighted energy usage over the mobile devices. Here, FM represents the computational frequency of mobile device, FE represents the computational frequency of edge device, beta represents channel transmission overhead, and P represents transmission power of remote edge devices while handling a small portion of the input data DM. We set some constraints to design a dynamic resource provisioning approach for minimizing the energy consumption. The transmitted power to the edge devices must be maximum. The CPU frequency of edge devices must also be maximum. Maximum of one edge device can be allotted for a mobile device. Latency constraint of a mobile device satisfies the sum of latency experienced by the mobile device and the offloading latency. And the final constraint is the computational frequency and the transmission power of remote edge devices must be non-negative. The contributions of our work are create a dynamic edge framework to assign edge devices to mobile devices at 6G networks utilizing the digital twin server as a representative. Together, these provide scalable. The contributions of our work are create a dynamic edge framework to assign edge devices to mobile devices at 6G networks utilizing the digital twin server as a representative. Together, these provide scalable 6G enabled edge networks with low latency and energy consumption. Design a deep Q learning based dynamic resource provisioning approach at the digital twin server that can deliver services at the network's edge or centralized cloud service based on user demands. Formulate a strategy to handle class imbalance data at the edge networks and validate with a classification model to analyze the mobile applications. The proposed intelligent mobile edge computing framework consists of a base station with a distributed set of mobile devices in an interference-free core network, a digital twin server as a mobile edge computing server, and a remote cloud server. In the proposed framework, the input data is partitioned into two parts. A small portion of the input data is handled by the mobile device, and the remaining data is offloaded to the distant edge devices for further computation. Here, the range of data is between 0 and 1. The equation shows the execution latency to execute the task DM-IM on the mobile device. Here DM is the data handled by the mobile device. IM represents the size of the input. CM represents the amount of computation needed. FM represents the processing frequency of mobile device. The energy consumption of mobile device without offloading is expressed in next equation. Here alpha represents hardware specific coefficient of a mobile device. In the proposed framework, when one mobile device corresponds to one remote device, uplink data transmission rate, SM, and corresponding energy consumption, PM, are defined in these equations. During offloading, the remaining data 1 minus dm is offloaded. Its uploading, transmission latency, and energy usage is described in these two equations. During offloading, the remaining data 1 minus dm is offloaded. Its uploading, transmission latency, and energy usage are described in these two equations. The execution latency and energy consumption of remote edge devices are described in next two equations. The total latency and energy consumption of mobile devices in the remote edge devices is presented here. Finally, the total latency and energy consumption of mobile devices on the remote edge devices is presented in next two equations. The proposed framework used deep queue network, which approximates the queue function at each timestamp. It includes three major components: state, action, and reward to solve the queue function. Here, a copy of the main queue network is called target network with frozen weights for a fixed number of steps. It calculates the target queue values when updating the main queue network. It also helps the deep queue network agent to converge more reliably by reducing the variance in queue value updates. The agent requires a policy for inferring the best action for the next move. At each state, the digital twin server moves to an action and collects its reward as per the policy when it reaches the next state. This repeated state action pair is resolved using Bellman's equation. To derive the optimal policy is defined this equation. The queue function captures the expected total reward received in a particular state while executing a particular action. The digital twin simulates the network's behavior under various conditions for resource provisioning. Dynamic resource provisioning can be achieved by integrating with a deep queue network to maximize the efficiency. It involves three steps. In the first step, the digital twin is created to mirror the real-world network environment, including devices, resources, and configurations. In the next step, the current state of the network condition is represented. Finally, as per the deep queue network, the digital twin server acts as an agent that allocates the input task over the distributed edge devices to get maximum reward from the environment. When the digital twin server interacts with the mobile network environment, it collects experiences and updates the queue network using the last function. This is defined in this equation. The gradient of this class is used to update the network weights theta. The class imbalance in the data generated by the mobile devices is handled by synthetic minority oversampling technique. Here, for each instance in the minority class dataset, the difference between the selected instance and its nearest neighbor is multiplied with a random value to get the synthetic samples. This is our proposed algorithm. At each time step, an action is simulated in a digital twin environment for a state selected using the epsilon greedy policy. The rewards are gathered from the environment before proceeding to the next state. Each experience is stored in the replay memory and a random mini batch of experiences is chosen for the training process. The target queue value is computed for each experience using the Bellman equation. To update the queue network, the loss is minimized to adjust weights and the queue value is improved. In the digital twin, the next state is set as the current state for the next iteration and the decay parameter is gradually decreased from the exploration to exploitation over time. The queue network weights are periodically copied to the target network to stabilize the training process. This training is continued over multiple episodes until the queue network converges, achieving optimal policies for resource provisioning, latency reduction, and energy efficiency. For simulation, the network parameters such as type of base station, bandwidth, carrier frequency, transmission power, number of mobile devices, and frequency of edge servers are initialized. The decay parameters such as state, action, discount factor, learning rate, exploration decay, minipad size, optimizer, memory size, episodes, and last function are also set during the experimentation. For validation, we used two imbalanced datasets, PIMA diabetes dataset and heart disease dataset. The performance of DT-DRP over these datasets is measured in terms of accuracy, loss, training time, latency, energy consumption, resource usage, and response time. For comparative analysis, we used four baseline algorithms based on 6G system-based architecture, user-centric system architecture, and digital twin network-based architecture. The experiment results show that the proposed method DT-DRP outperforms the other methods For PIMA diabetes dataset, it reached 98% of utilization at 20 seconds, which is 2 to 6% higher than the alternatives. For the heart disease dataset, DT-DRP again leads, achieving 85% of utilization at 20 seconds, outperforming the other methods by 2 to 5%. DT-DRP also maintains significantly lower response times compared to the baseline models as the task volume increases. This shows that the DT architecture allows to adjust resources efficiently in real time, resulting in consistently lower response times. The energy consumption across various resource provisioning techniques for different network conditions are measured. For PIMA diabetes dataset, DT-DRP consistently outperforms all other methods. In stable conditions, it consumes the least energy of 50 joules at 100 episodes, dropping to 38 joules at 400 episodes. For the heart disease dataset, DT-DRP also leads in energy efficiency, consuming 45 joules at 100 episodes and 38 joules at 400 episodes. Hence, DT-DRP achieves the lowest energy consumption across both datasets, and this proved the ability of the proposed method to dynamically respond to the network demands. The average latency for various resource provisioning techniques is compared with the DT-DRP with the increasing task volumes. For PIMA diabetes dataset, DT-DRP consistently demonstrates the lowest latency across all task volumes with a notable reduction from 27 milliseconds at 100 tasks to 50 milliseconds at 500 tasks. For heart disease dataset, DT-DRP reduces latency 30 milliseconds at 100 tasks and reduced to 55 milliseconds at 500 tasks. During the DQN training, the agent explores more when the epsilon decay is 1 and it learns to exploit the environment when it gradually reduces to 0.01. During the first episode, DT-DRP selects action randomly. After a few episodes, DT-DRP receives maximum reward and derives optimal decisions to optimize the intelligent decision-making process. DT-DRP explores the optimized reward for PIMA diabetes dataset and heart disease dataset rather than conventional Q-learning techniques. DT-DRP approach demonstrates its performance in terms of accuracy, loss reduction, and convergence speed over baseline methods on both PIMA diabetes dataset and heart disease dataset. The training time comparison for the PIMA diabetes dataset across different methods shows that the DT-DRP demonstrates a fastest training time, reaching 17 seconds at 400 episodes and reaching 8 seconds at 400 episodes for the heart disease dataset. We thank our mentor and professor Dr. Moina Kadigari from School of Data Science, ISER Thiruvananthapuram for supporting and guiding this research work. This work is supported by Telecom Technology Development Fund of Department of Telecom. Thank you.